Hello students, welcome to chemistry class. Today's class, I'm going to explain you about high performance liquid chromatography. Liquid chromatography, it is carried out with columns more than 1 centimeter in diameter. The flow of the mobile phase occurs due to gravity, though it is occasionally accelerated by hydrostatic pressure. The flow rate is less than 60 ml per hour. And if column cross section is 1 centimeter square, again that will be equal to linear flow of less than 0.02 centimeter per second. So how this is carried out, this high pressure liquid chromatography, it is carried out in detail, we'll see. So this is a new technique, high performance liquid chromatography, generally we call HPLC, developed as a versatile technique to meet present needs. This technique has been possible through the knowledge of accumulated technique from gas chromatography. This technique for HPLC make possible to control the solute retention and you can get more selective. So we'll see what is chromatography, the terms, basic terms involved, and later on HPLC in detail will study the instrumentation. Chromatography is a technique which separates components in a mixture due to differing time taken for each component to travel through the stationary phase when carried through it by a mobile phase. So chromatography is a technique which it's a separation technique for the mixtures. So due to differing time taken, the compounds travel through the stationary phase, which is being carried out by mobile phase. So chromatographic system, it generally consists of mobile phase, stationary phase. So liquid or gaseous and all this flows over through the stationary phase is called the mobile phase. That is the liquid one or the gaseous one. It flows over through the stationary phase. Now what is the stationary phase? The solid or the liquid can be stationary phase. Stationary phase, it can be in the solid state or the liquid state. As a mobile phase, it should definitely be mobile, so it can be in the liquid or the gaseous state. So stationary phase, it is stationary, so that can be solid or a liquid solid mixture which is immobilized. So that is the stationary phase. And what is analyte? The substance to be separated during chromatography, the one which we are analyzing is called analyte. Immobilized phase. Here I told you stationary phase which is immobilized. So stationary phase which is immobilized on support particles or on the inner walls of the column tubing are called as the immobilized phase. Okay, so taking the support particles in the column, that is nothing but you treat even with some of the solvent, and that is the immobilized phase called as the stationary phase. And some of the chromatographic terms, mobile phase and effluent. Phase which moves in a definite direction. Mobile phase. Phase which moves in a definite direction is nothing but the mobile phase. It can be liquid, fluids, or the gases. And this mobile phase consists of sample that is being separated, analyzed, and the solvent that moves the sample through the column. Effluent, mobile phase that is leaving the column is called effluent. Now, different types of chromatographic methods. So we have seen the basic terms, what is analyte, immobilized phase, mobile phase, effluent. So mobile phase that is leaving the column is nothing but effluent. And what is a mobile phase, what is a stationary phase, we have seen. Now, different types of chromatographies we'll study. So, paper chromatography, liquid chromatography, gas chromatography, high performance liquid chromatography. Already the paper chromatography is explained for you, and column chromatography is also explained for you. Thin layer chromatography also explained for you. Now we'll see HPLC, high performance liquid chromatography, in detail. So this is the introduction before I start HPLC. Now, what is HPLC? HPLC, it stands for high performance liquid chromatography. Sometimes it is referred to as high pressure liquid chromatography. So high performance is there as well as high pressure is applied. So high performance liquid chromatography, it is a powerful tool in analyzing. It yields high performance, high speed compared to traditional columns. Traditional column chromatographies. Last class, I explained you about the column chromatography. So that is the traditional method and this is the advanced method. So here you'll be having high performance. It is a powerful tool in its performance and it is moreover high speed. So it is forcefully pumping the mobile phase. HPLC is a chromatographic technique that can separate a mixture of compounds. It is used in biochemistry and analytical chemistry to identify, quantify, and purify the individual components of a mixture. It is used in biochemistry, analytical chemistry to identify, quantify, purify. You identify, and then how much is there, and the purity cannot be checked for the components of the mixture. It is a form of column chromatography where you separate, identify, quantify the components. Developed in 1970. It is mostly used analytical separation technique. It is more advanced due to its speed and its high performance. High performance liquid chromatography is an extension of conventional liquid chromatography. Extension conventional liquid chromatography. So the traditional method of detecting a column separation is also discontinuous and tedious. So conventional liquid chromatography, the fractions of the column effluents collected with automatic fraction collectors. So therefore, with increasing demands on the purity of the industrial and pharmaceutical products, and growing interest in the analysis of biological and environmental samples, a versatile, a rapid, versatile separation technique has become needed for us. And the new technique, it's nothing but the HPLC, high performance liquid chromatography. It was developed as a versatile technique to meet present needs. And this technique has become possible through the knowledge of accumulated from the techniques of gas chromatography. So this technique, it is possible to control the solute retention and achieve better selectivity. It is powerful tool in the analytical techniques. Columns are tightly packed and the eluent is forced through the column under high pressure up to 5000 psi by a pump. And it allows HPLC allows to use a very small particle size for column packing material. And it gives much greater surface area for interaction between a stationary phase and the molecules flowing through it. So it requires small particles for the column packing and thereby we can achieve the greater surface area. Greater surface area and thereby interactions between the stationary phase and the molecules following through it can be achieved. It allows a much better separation for the components of the mixture. So better separation of the components of the mixture can be allowed. Now HPLC technique utilizes liquid mobile phase to separate the mixture. This technique utilizes liquid mobile phase to separate the mixture. Analytes are first discovered in a solvent, then through the column under high pressure of up to 400 atmospheres. So analytes are dissolved in the solvent, then they are through the column with high pressure of 400 atmosphere. Mixture is resolved into its components in the column. Mixture is resolved into its components in the column in this technique. The total separation time is often 5 or 10 minutes rather than hours or even days. We have previously in the traditional method it used to take hours and sometimes days. So for this HPLC it has become more simple that it is taking 5 or 10 minutes. See how much difference has come in the separation. So it is required for some separations by gravity flow with larger systems. Okay. Now we'll see the schematic diagram. How the schematic diagram will see the flow scheme of the HPLC. Here you can see the solvent reservoir and then pump that produces high pressure. So as the solvent reservoir travels, pump will be producing more pressure to this solvent reservoir. So here we inject the sample. Here this is the reservoir, this mobile phase will be. So as you inject the sample, the solvent reservoir flows with high pressure and thereby it comes into HPLC tube. Immediately in this column, the separation of the components takes place and thereby it is detected and the processing unit, you get the processor signal and it is displayed here. Whatever waste is there, that waste will go out. Okay. Now we'll see the principle for this one. Here the principle is, the main drawback of, as mentioned earlier, this classical liquid chromatography, it is slow. So between the two phases. Therefore, in this HPLC higher functional efficiency was achieved by increasing rate of mass transfer and rate of equilibrium of the solutes between the mobile and the stationary phases. Here, the HPLC and the conventional liquid column chromatography will not differ fundamentally in basic, a physiochemical principle. High rate of mass transfer and high rate of equilibration of the solute between the phases will be achieved in HPLC using the column of packing, using the packing of the column materials, which is with the small sized particles. Yeah, employing these pumps, you'll be having the pumps, employing these pumps. Okay, so with high pressure, yeah, nearly 7,000 7,000 psi separation times when compared to the gas liquid chromatography is achieved. This technique can be extended to separation systems employed in different types of other liquid chromatography methods. So these adsorption, partition, ion exchange methods, and gel exclusion. So these all come under the different types of liquid column chromatographies. So this technique is extended. See, I'm telling you once again, I'm repeating. This technique, it is extended to all separation systems employed in different types of other liquid column chromatography methods. These are nothing but adsorption, partition, ion exchange methods, gel exclusion, all these methods, this technique of HPLC is employed. So this high pressure liquid chromatography or high performance liquid chromatography can be done. Now we'll see the instrumentation in detail. Components that you're having is the pump I told you, which gives high pressure. Here, pump, okay, produces high pressure. Okay, next injector. The components of this HPLC are pump you're having, and you're having the injector, and the next one is the column, detector, recorder. These are the basic components and which type of solvent we are taking. So this is the schematic diagram of the HPLC. Instrumentation is most important. Now in this, first we'll see about the, here we'll see about the pump, then the sample injector, which type of injectors we'll be using, and what is the column, what is the detector, and what are the recorders we are using here. The functions we'll see: pump, injector, column, detector, recorder, or the data system. Here you can see the storage. Here this is the mobile phase solvent reservoirs. Okay, so preparation of the effluent mixtures will be done here. Here this is the pump providing high pressure, total control unit, your sample injector, auto sampler, and this is the column. This is the injection valve. Here it is detector, and thereby after recording, detector will detect, and there will be a display. So operation mode, we can see isocritic constant effluent composition, gradient continuous variation effluent. So these different operation modes we can observe. So a pump. Pump forces the mobile phase through the column at a much greater velocity than gravity flow columns. A pump forces the mobile phase through the column at much greater velocity than gravity flow columns. The pump can be pneumatic syringe type. The pump can be the pump can be pneumatic or the syringe type, reciprocating or hydraulic samplifier. Okay, so the pump forces the mobile phase through the column at much greater velocity than the gravity flow columns. Than the gravity flow columns. So pump forces mobile phase through the column at greater velocity than the gravity flows. Yeah, because yeah, this why it is doing, because this pump, it's forcing the mobile phase through the column with great velocity than gravity flow columns. This is the traditional one, and this is the recent one which we are using. Here in this pump, the pressure you're applying, due to more pressure, great velocity will be there. So for the traditional ones, only through the gravitational force it is slow. So these pumps can be pneumatic syringe type, reciprocating, hydraulic amplifier. Next, pneumatic pumps are used for the pre-operative purposes. The most widely used pump today is the multi-head pump. Most widely used pump today is the multi-head pump with two or more reciprocating pistons. So widely we are using this pump. It is a multi-headed pump. So reciprocating pistons are more, which is useful for the, which is very much useful. So that type of pumps we are using. Now these pumps are designed in order to maintain a stable flow rate, avoiding pulsations, even when the composition of the mobile phase varies. The flow range is 0.01 to 10 ml per minute. So stable, in order to maintain the stable flow rate and avoiding pulsations when composition of the mobile phase is varying. So Different mobile phases will be same, sometimes the same mobile phase, sometimes the mobile phase will be changing. So at that time, to avoid the pulsations also, it is designed for the stable flow rate. The pumps are designed in such a way that you should have the stable flow rate. General flow rate is 0.01 to 10 ml per minute. Here you can see a HPLC pump. How? On a button and this pump. So generally pumps, what they do, you have seen the diagram. So this pump produces high pressure. Okay. So now we'll see the injectors. Injector, what the injectors do is they inject the liquid sample with the range of zero point 0.1 to 100 ml of volume under the high pressure. So inject the liquid sample within the range of 0.1 to 100 ml of volume under high pressure. So produces minimum band broadening, produces possible flow disturbances, and volume must be small. Very less volume should be injected. So these are the basic functions for an injector. So it injects the liquid sample with the range of 0.1 to 100 ml of volume, and that is at high pressure it does. It produces minimum band broadening, and this injector produces possible flow disturbances. So you have to look onto that. The production of the possible flow disturbances should be avoided. So the volume must be small. So it should have minimum band broadening. Such type of injectors are used. Here you can see example. Here this is the injector, model injector, where you are injecting the sample. Here, this is the injector, sample injection. Here you can see. This is the point where you put the injector in the machine, model injector. Here you place it. Here, the syringe type. Okay, so this is the needle port, sample loop, this one, and to the column it is connected. Okay, this is the syringe, this is the needle port, loading portion, this is the sample loop, injecting, stator phase, rotor seal, again syringe needle, syringe. Okay, from the pump, it's going on. This is the injector. Now we'll see the columns. How this is the injector you have seen, and columns. Smooth bore stainless steel or a heavy walled glass tubing, or the heavy walled glass tubing can be used. And hundreds of packing columns differing in the size and packing are available from the manufacturer. So hundreds of packed columns differing in size and packing are available from the manufacturer. Okay, so this type of columns are used. Now we'll see the small bore stainless steel with the picks. We'll see steel heavy walled glass tubing columns, how they are different sizes. You can see. Example, column packing vary in size 3 to 10 here 3 to 10 centimeters. But the small particles were micrometers printing from. He uses mostly for the analytical separation and large ones for the preparative separation. Okay, so the smooth bore stainless steel or the heavy walled glass tubing here. See here, these are the different type. They are the smooth. You can see the surface is so smooth, and they're stainless steel, heavy walled glass tubing. You can see hundreds of packed columns differing in the size and packing are available from the manufacturer. hundreds of packed columns which are differing in size and are packing are available from manufacturers. Example, column packing generally varies in size 3 to 20 micrometers with small particles used mostly for analytical separations and the large ones preparative separation for the preparative separation. The most common material used for column packing is silica gel. Your polar groups generally get separated in here as silica gel, and for the non-polar groups we take the alumina. Here you can see the columns. Stainless steel. Here, add heavy walled glass tubing will be there inside. Okay. Now we'll see the detectors. How the detectors are used. HPLC detectors monitor the elute as it leaves the column. It elutes as it leaves the column, and it produces an electronic signal proportional to the concentration of each separated component. So detectors monitor the elute as it leaves the column, and it produces the electrical signal proportional to the concentration of each separated compound. So detector, crucial in trace analysis, high sensitivity, and it is fast response, simplifies quantitation, insensitive to changes in the type of solvent, flow rate and temperature. So it is crucial in trace analysis, this detector, and it is highly sensitive. It gives a fast response, simplifies the quantitation, how much quantity of a complex of a mixture is that is being easily simplified, insensitive to the changes in the type of solvents, whatever may be the solvent, how many ever change you do the changes for the solvent. As you change the solvent, this is insensitive, this detector, and the flow rate and the temperature also it is insensitive. So some of the examples we'll see what are being used. The most widely used detection methods are spectrophotometer, fluorometers, electrochemical detectors, mass spectrometer, refractive index. So these are the mostly used detection methods. Yes, spectrophotometer, here it is the absorbance principle and analytes that absorb the UV or the visible light. Fluorometers measures the fluorescence. Analyte must be a fluorescent. Electrochemical detectors used when electrochemical measures oxidation and reduction takes place for the analyte. It is used for the catecholamines. Mass spectrometer, it detects the ions after separation by mass to the charge ratio. Analyte must be converted to the ionized form. So that ionized M by Z values will be recorded. This is the main principle, and the analyte, it should be able to convert to the ionized form. Thereby taking the M by Z value, the mass spectrometer, it detects the signal. Now refractometer type of detector can be used in HPLC. It measures the change in refractive index. It detects most of the components but relatively low sensitive. So those are the types: fluorescence detector, refractive detector, electrical detector, conductivity detector, density detector, dielectric constant detector, vapor pressure detector. Such type different we can use. Okay, so I'm just giving after completion of this detectors, overall view we'll see for the HPLC. So here from how this it is taking place, we'll see in the diagram. I have given you the all the parts of the HPLC. Now a schematic diagram we'll see, and how the basic process of HPLC separation is doing. We'll see. So from the main components of HPLC in the block diagram you have seen, from the solvent reservoir, pump delivers a constant from the solvent reservoir. Pump delivers a constant flow of the solvent at the pressure up to 500 psi. The inlet pressure of the column is measured with a pressure gauge. After leaving the column, the sample components are sensitized. Here you can see from the solvent reservoir, it delivers constant flow of the solvent at the pressure of 500. Now inlet pressure of the column with the pressure gauge. After leaving the column, the sample components are sensitized and monitored by the recorder. If the samples are isolated at the fraction collector, it is attached to the recorder. The nature of the column materials, the geometry of the column, and the connections are so critical. So the columns are operated at the ambient temperatures, but elevated temperatures are used if needed. Okay. The sample injector, column, detector are all thermostatic. Mobile phase temperature must be adjusted. Mobile phase temperature must be adjusted prior to the introduction to the sample. Okay, so the pressure it's needed. Since the columns are thin long, the good solvent compatibility is also needed. Pumps are also available which can provide pressures at high pressures. Heat generated operating at high pressures are removed. Okay, the LM system is introduced into the columns through reservoirs. These must contain degassing system and attached to the element dissolved layers. The column shall have inner diameter of about 4.5 mm, a wall thickness of 0.16 centimeter, and the length of 10 to 15 centimeters are needed for analytical work. Column of ID of 20 mm and length of 50 centimeters are needed for preparative. So the materials used for the column stationary phases. Column stationary phases are porous beads and pellicular beads. Pellicular beads. So these are the different types. You can separate the vitamins, benzoic acids, drugs, amines, oligosaccharides, and fat soluble vitamins, fatty acids, steroids, drugs, etc. So the mobile phases which we are using are chloroform hexane, only hexane, hexane with isopropanol, acetone, chloroform with isopropanol. So such type different we can use the mobile phases. Now, different types. So we have seen the instrumentation, what are the components of the system and how it's working. We have seen. Now in the HPLC, two types depending on the relative polarity of the solvent and stationary phase. There are two variants in use in the HPLC. Normal phase HPLC and utilizes polar adsorbent surface and non-polar eluent. Polar substances in the mixture sticks to the polar adsorbent than non-polar. So normal phase HPLC it uses polar adsorbent surface and non-polar eluent. Okay, so polar adsorbent surface with non-polar eluent. Polar substance in the mixture sticks to the polar adsorbent than non-polar. Generally, polar substance of the mixture it sticks to the polar adsorbent than the non-polar. A non-polar one will pass more quickly through the column. Now coming to the reverse phase HPLC, it utilizes non-polar adsorbent surface and polar eluent. So the attraction between the non-polar component in the mixture and non-polar adsorbent. So there is attraction between non-polar and the non-polar. Compound is non-polar and the adsorbent is also non-polar. It uses non-polar adsorbent surface and the polar eluent surface. Solars, yeah, the solvents which are used already explained for you. The solvents which we are using in the mobile phase, hexane, heptane, cyclohexane, CCl4, benzene, toluene, diethyl ether, uh, chloroform, etc. So adsorbents which we are using in the stationary phase are silica gel, alumina, silite, cellulose powder, ion exchange, cellulose, and starch. Now, what the principle behind the total instrumentation is here the time taken, retention time, time taken for a particular compound to travel the column to detector. So, time taken for a particular compound to travel through the column to the detector. So, from injection to the detector, how it's traveling and what is the time as it is passing the column, that is retention time. From the time at which the sample is injected to the point at which the display shows a maximum peak height for that compound. So from that time, how much time it is traveling, at that time the sample is injected to the point at which the display shows maximum peak height for that component. Now, different separations, as I have explained you, different separations can be done in this HPLC. Adsorption can be done, ion exchange can be done, and size exclusion can be done. So, competition for the adsorption sites occur between the molecules of the mixture to be separated and the molecules of the mobile phase. Mobile phase can either be a single solvent or two or more solvents. It depends on the analytes to be dissolved. Speed of the migration of the component, speed of the migration of the component along the column, it depends on adsorptive affinity. Speed of the column, speed of the migration of the component along the column, it depends on the adsorptive affinity. This is adsorption chromatography. Now, ion exchange chromatography. Molecules separated according to their ionic charges in the process known as ion exchange chromatography. Ion exchange resins are used as the column packing material. Ion exchange resins are used as the column packing material. This method it is used for separation of ionic species such as amino acids. So they are separated using the ionic charges in a process and known as ion exchange chromatography. Ion exchange resins are used for this column packing, and it is used for separation of the ionic species such as amino acids, where you are having amino group and the acid group. Here you can see ion exchange, ions, plus and the minus, counter ions. Here your injection. Here the adsorption takes place, counter ions. Adsorption displacement of the counter ions. Then elution. So mobile phase additives and competition. Now size exclusion chromatography. It is known as size exclusion chromatography is known as gel permeation chromatography or gel filtration chromatography. Packing material very small pore is used. Precisely controlled pore size materials in the column are used. Large size molecules such as polymers are physically prevented from passing through the column. So according to the size exclusion chromatography is performed. Otherwise called as a gel permeation chromatography or gel filtration. Size exclusion, gel permeation, gel filtration, same. Packing material, it's very small pore is used. Very small pores are used. Precisely controlled pore size materials in the column. Large molecules, polymers, are physically prevented from passing through the column in this size exclusion chromatography. Applications, coming to the applications, HPLC it is used for chemistry and biochemistry, research analyzing complex mixtures. So, purifying chemical components, quality control to ensure the purity of a raw material, analyzing air and water pollutants can be done in this HPLC. You can even monitor materials that may jeopardize occupational safety or healthy. Monitoring pesticide levels in the environment can be done using HPLC. And you can go for the survey of the food and the drug products. You can identify, confiscated narcotics and to determine the amount of such chemical components in the new drugs in the pharmaceutics can be done using HPLC. HPLC as compared to the classical technique will see small diameter and it is reusable stainless steel columns. A column packing with very small particles are done. A control flow of the mobile phase, a constant rate of flow, precise sample introduction is there. So HPLC, it's a good pumping system. special continuous flow detectors, and can handle the small flow rates and detect very small amounts. It is the rapid analysis and it is of high resolution. Now we'll see the disadvantages of the HPLC. The cost, it is expensive. So that is a disadvantage for us. It is complex, though it is fast and more perfect. So resolution is more, sensitivity is more, it is high speed, but the complexity is also more. That is a disadvantage. The cost is also high. So low sensitivity for some compounds you can see. Irreversibly adsorbed components do not be detected. And co-elution difficult to detect. So and along with our components, the other components can also be eluted, which is difficult to detect. And it is irreversible adsorbed components not detected. So the modern day technique is greatly enhanced in terms of selectivity, resolution through mini authorization, and use of very elaborate stationary phases are achieved in this HPLC. HPLC is widely used for separation of molecules in pharmaceutical, biological, food, environmental, and industrial process. So this is the overall explanation for you on HPLC. So just repeating the main points of the high pressure liquid chromatography. So actually we have seen chromatography, what is chromatography, and the basic terms of the chromatography we have seen: mobile phase, stationary phase, analyte, immobilized phase, mobile phase, effluent. Types of chromatographies we have seen. In that, today's class is about the HPLC. So, what is HPLC, how it was developed, and how important is this technique was discussed. A schematic diagram for HPLC is explained, and the components pump, injector, column, detector, recorder are explained, and the diagrams shown while explaining in detail about all these components of the system. Thereupon, after this one, detectors using all the components using the types. So normal phase HPLC, reverse phase HPLC, we've seen what are the solutions that we are using, what are the stationary phase, what is the mobile phases we are using for this HPLC, what is the retention time, how it is employed for different chromatographic separations, adsorption chromatography, ion exchange chromatography, size exclusion chromatography are explained in this session. And later on, applications are explained and how it is more good than the classical technique is also explained. Advantages and the disadvantages of the HPLC are given. Overall, I hope you have understood this my HPLC session. Thank you, everybody.